Welcome, friends. I hope you're as excited as I am to explore the rich and rewarding topic of enhancing language models through optimized test-time computation. Today, we're going to discuss an insightful piece of research titled Scaling LLM Test-Time Compute Optimally Can Be More Effective Than Scaling Model Parameters, conducted by colleagues at UC Berkeley and Google DeepMind. This study investigates an alternative approach to improving the performance of large language models by intelligently using additional computation when generating responses, rather than simply increasing the size of the models themselves. Traditionally, when seeking to enhance an LLM's capabilities, especially on complex tasks like mathematical reasoning, we might increase its number of parameters. Think of this as adding more components to a machine to boost its output. However, larger models come with significant drawbacks. They require more storage, consume more memory, and demand more energy. This can make them less practical for widespread use, particularly in environments with limited computational resources. The researchers explored a different path. They asked, if we allocate a fixed but substantial amount of additional computation to an LLM when it's generating an answer, a concept known as test-time computation, how much can we improve its performance on challenging prompts? Essentially, can we make a model think harder on difficult problems by giving it more time and resources during the actual task, rather than making it inherently larger? Their findings are quite interesting. They discovered that, in some cases, scaling test-time computation can lead to better performance than merely increasing the model's parameters. This approach not only has the potential to improve the model's responses, but also opens up new possibilities for creating self-improving AI agents capable of operating efficiently in real-world scenarios. To investigate this, they analyzed two primary strategies for utilizing additional test-time computation. First, they looked at searching with a verifier model. In this strategy, the language model generates multiple candidate answers to a prompt. A separate system, known as a verifier, then evaluates these candidates to select the most accurate one. The verifier assesses each potential response by predicting its correctness, much like an expert checking students' solutions to identify the best one. This method allows the model to explore various possible answers and rely on the verifier to guide it toward the most promising one. Second, they examined adaptive updating of the model's responses. Rather than settling on an initial answer, the model iteratively refines its response based on feedback. It's akin to writing a first draft, reviewing it critically, and making improvements until the final version meets a higher standard. This approach leverages the model's ability to critique and revise its own output, enhancing the quality of the response through successive iterations. An important insight from their research is that the effectiveness of these methods depends on the difficulty of the prompt. For less challenging questions, having the model refine its answers iteratively led to significant improvements. The model could make minor adjustments to reach a correct solution efficiently. However, for more difficult problems, generating a diverse set of answers and employing the verifier to select the best one proved more effective. This approach allowed the model to explore different problem-solving strategies that it might not consider through iterative refinement alone. Based on these observations, the researchers proposed a compute-optimal scaling strategy. Instead of using a one-size-fits-all approach, this strategy adapts the allocation of test-time computation based on the estimated difficulty of each prompt. By assessing how challenging a question is for the model, we can decide whether to focus on iterative refinement or extensive exploration with the verifier. This adaptive method optimizes the use of computational resources, making the process more efficient. Implementing this compute optimal strategy, they achieved significant improvements. They found that test-time computation could be used more than 4 times more efficiently compared to traditional methods like best-of-n sampling, where the best answer is chosen from several independent attempts. Remarkably, in some cases, a smaller model using this optimized test-time computation outperformed a much larger model. Specifically, one that was 14 times bigger in terms of parameters. This finding is noteworthy because it suggests that by intelligently allocating computational effort during response generation, we can enhance performance without the need for increasingly large models. Smaller models with efficient test-time computation are more practical to deploy, requiring less storage and energy. This makes them suitable for a wider range of applications, including devices with limited computational capacity. Furthermore, this approach has implications for the future of AI development. It points toward the possibility of creating AI agents that can self-improve by effectively using their computational resources to tackle complex tasks. By focusing on how we use computation, rather than just increasing the model size, we can develop systems that are both powerful and efficient. In conclusion, this research highlights the potential of optimized test-time computation as a means to enhance language model performance. By adapting our strategies based on the difficulty of the tasks and making smart use of computational resources, we can achieve significant improvements without the drawbacks of scaling up model parameters. This underscores the importance of innovation in AI methods, reminding us that sometimes it's not just about having more power, but about using the power we have more wisely. Thank you for joining me on this exploration of an intriguing development in language model research. I hope this discussion has shed light on how strategic computation can elevate the capabilities of AI systems. Until next time, keep exploring and stay curious.